Hi, in this video, we're going to take a look at classification neural networks. Now, we're going to approach them as an extension of logistic regression. So this is a logistic regression series. And what I want to do, I want to show you how there's a connection between logistic regression and neural networks, classification neural networks, two levels. That connection is that there's an additional layer between the predictor variables and the target variables in the neural network. And that additional layer is not in a generalized linear model, not in the logistic regression model. And in fact, what we call the activation function in neural networks is actually the inverse of the link function in generalized linear models. So there's a direct relationship. Now, my warning against neural networks, they're very complicated. You can overfit. There's a lot of problems with them. They're super, super powerful when they're used correctly, but they get a lot more love than their utility actually justifies, in my opinion. All right, so let's dig into it. So neural networks are a foundational tool in machine learning at this point. They originated from the concept of simulating the neuron-like structure in the human brain. These models have shown that they have immense power in pattern recognition. And so, pattern recognition, that's really what statistical learning and machine learning is. So for pattern recognition, regression, classification, and more. At their core, neural networks can be viewed as a generalization of generalized linear model. All right, so here's my warning against neural networks. So in my experience, neural networks is not the best choice for spreadsheet problems, just flat out. So if I'm working on a spreadsheet problem, that is, I have like a single table, from a SQL data pull or an Excel spreadsheet, or any other situation that could get a flat file, almost always a neural network is not the best choice. Just over and over and over, I've tried neural networks and it's just never been the best way to go. When I have had better accuracy off of neural networks, it wasn't by much, and it just took a lot more work to get to that point. So if it's more effort for not much more benefit, not the best way to go. My personal experience is that if you can represent your data with a flat file, like pretty directly, somebody hands you an Excel spreadsheet, if you're pulling the table from a SQL database, something like that, you're probably better off not using a neural network for most situations. This isn't, of course, this isn't 100% true because people are using neural networks very, very well. But for most problems that you actually tackle and work on, there's simpler approaches that will give you at least as good of a solution. So what are the problems with neural networks? First and foremost, they're prone to overfitting. They're super flexible, but that flexibility comes at a cost that we can overfit. They require a lot of data. Neural networks are the apex of black box models. When your stakeholder asks, why did the model do X, Y, Z? You're going to have to say, I don't know, because it's a neural network, it's black box. I have no idea what's going on. There's a lot more data prep, not a lot more, there's more data prep required because neural networks just can't handle situations that like tree models could handle very easily. Neural networks don't do well with outliers. Also, they require a lot more tuning. We have to decide the number of layers, number of hidden nodes in each layer, what our activation functions are, our skip layers, if we're going to, our bias, if that's the intercept, epochs where I just run through again, etc. So for my experience professionally, for the amount of work, neural networks just aren't worth it. That being said, neural networks are super powerful when used correctly. It's just they have a very specific lane to work with. They can handle non-spreadsheet problems very, very well. When I say non-spreadsheet problems, I'm talking about images, recordings, movies, like things that aren't like a spreadsheet. Then if I've got a large number of them, man, it can knock some stuff out. It is extraordinary what neural networks can do. If I am doing a spreadsheet problem, then a single neural network layer, a single hidden layer with the square root of the number of predictors is about where I need to be. I didn't come up with that number. I read that somewhere in a blog post. I wish I could give credit to the person who said this, but I read that, I tried it, and I evaluated it, against some other different models, and I find that that's a correct statement. That the square root of the number of your predictors in one hidden node is usually enough to get as accurate as you're going to get with a neural network. And also by capping the number of hidden nodes you have, you're making sure that you're protecting yourself from overfitting. All right, so a neural network comprises layers of interconnected neurons or nodes, and each connection between two neurons has an associated weight. In statistics, in regression, we call the weight the coefficient, but in neural networks, we call the coefficient a weight, which adjusts during the learning process. Each neuron processes its input through an activation function. The activation function is the inverse of a link function, allowing the network to capture nonlinear patterns. All right, so let's go ahead and draw a connection, to draw a picture to help indicate what a generalized linear model looks like. So let's say I've got 3 predictor variables, 1 target variable, and I want to draw a neural network diagram for my generalized linear model. So it's pretty simple. I've got 3 predictor variables, 1 target variable, which we call the output. And this is what a generalized linear model looks like, that we've got these 3 going in. Each of these has a weight, which is a coefficient. The bias is the intercept, and the activation function is the inverse of the link function for a generalized linear model. And so anytime I have a generalized linear model, I can represent it directly as a neural network with no hidden nodes, with no hidden layers. All right, so the neurons as generalized linear models, at the core, each neuron can be considered a generalized linear model. The output of a neuron is the result of a weighted sum of its inputs transformed by the activation function. So let's say for neuron I, the input is x sub I with weight associated of wi. The weighted sum can be represented here, and the weights can be negative for this. And the activation function A is then processes this sum here like this. Each node in the graph with an arrow coming from it is an independent variable in a generalized linear model. Each node in the graph with an arrow going into it is the response variable in a generalized linear model. All right, so what I'm saying here is that if I look at just this neuron right here, and so here, this is my hidden layer, here is the neuron. Notice I've got input going here, I've got input going here, and I have input going here. If I look at only this neuron and these 3 input variables, these 3 input variables and neuron actually forms a generalized linear model on its own. Now, if I look at this neuron and these 3 inputs, I'll notice I have the same situation. The inputs are going into the neurons. And so, in fact, these inputs, along with this one neuron, also forms a generalized linear model. And now, if I look at this neuron and this neuron, along with this output, I see that these 2 neurons and the output form a generalized linear model also. So effectively, I have 3 generalized linear models going on in this picture right now. Each time I have an arrow that corresponds to a non-negative weight, which is it's a coefficient in generalized linear models. All of the inputs that are shooting arrows into something to the right, all of those are being grouped together and converted using the activation function, which is the inverse of a link function. And so I see pretty directly that this is really just a generalized linear model situation. It's a tangled bag of generalized linear models. So the activation functions and link functions are inverses of each other. and they describe how the expected value of the response relates to the linear predictors in the model. And realize that I've got, like in this diagram, I have 3 generalized linear models floating around. Activation functions in neural networks can be thought as the inverse of the link function. Now, there's a sticking point with this, in that not all activation functions have an inverse. Like if I'm using like a piecewise defined function where it's like constantly 0 and then there's a straight line slope, that won't have an inverse operation. But if it does, if it has an inverse function, then that inverse could be used potentially as a link function. The bias term and intercepts. So what we call an intercept in statistics is called a bias in neural networks. So the intercept allows the line to not necessarily pass through the origin. Similarly, bias in a neural network shifts the output of the neuron, allowing greater flexibility. And so here, this is just one representation of it. Now, the weights of the weights of a neural network are coefficients, and every time I see an arrow, I know that I have a non-zero coefficient, a non-zero weight. Now, for the architecture of neural networks, the architecture of a neural network defines its depth, that is the number of layers, its width, the number of neurons in a layer, and the connection patterns. The 3 primary layers are the input layer, the hidden layer or layers, and the output layer. The input layer, this is where all of your predictor variables are. This is where the data is introduced into the network. The number of nodes typically matches the number of features in the data set, but it could be more if I went through and did like a squaring or a square root transformation of something. The hidden layers, layer between the input and the output layers. Neural networks can have multiple hidden layers, making them deep, leading to the term deep learning. And the output layer, this is my target variable layer. This provides the final output. For a single target variable neural network, if I have regression, I have a single layer. For classification, I'll actually have a neuron for each class. And so effectively in this situation, what I'm doing is if I have, let's say, 5 levels going on of my target variable, I'll have this variable versus not this variable versus not this variable, this level versus not this level, this level versus not this level, this level versus not this level. So we're going to dummy code the levels of our target variable to be able to get this, which is similar to some other model structures that we talked about previously in other videos. So for data preparation, okay, neural networks cannot handle missing values. Generalized linear models can't handle them either. It's basically the same problem. All the problems you have in generalized linear models and multiple linear regression come to bear more so in neural networks. And so I have to do imputation, or I have to omit observations that have missing predictor variables, or I could remove features with missing values. I have to do either have to omit something, either a row or a column, or I have to make up fake data by imputation. Whatever, depends on my situation. Now, standardization of input variables is a big deal. This is a really probably bigger deal here than anywhere else. Neural networks tend to converge faster and perform better when all independent variables are standardized. Generally speaking, most software are going to want things to be standardized to 0, 1. So the minimum value gets converted to 0, maximum value gets converted to 1, and then you have a continuation in between. Now, a problem with this, if you think about this for a moment, if I'm doing statistics, I'm not talking about like pictures, because if I'm dealing with like pixels, I know that everything's from 0 to 255. But if I'm talking about actual real world data, let's say I'm talking about a person's height, in my data set, I'll go collect height. Well, next, when I get data that I need to make a prediction on, I can come upon someone who's taller than anyone that was in my data. Or I could come upon someone who's shorter than anyone who is in my data. And so now my my transformation doesn't take into account those extreme cases. So just something to be mindful of. Now, for fitting the weights, neural networks learn by iteratively adjusting the weights on the connections to minimize the difference between the predicted and actual output. And this is the training process. Now, how is this accomplished? This is done through backpropagation. All right, so backpropagation is a supervised learning algorithm used for training neural networks. It's a method used to calculate gradient of the loss function concerning each weight. Now, here is kind of a brief description of it. We take an input of a data set sample to the neural network, compute the output of the network, a forward pass. So we start out with just some either randomly guessed or some default values of the coefficients of the weights, push it forward. We compute the predicted output here and calculate the error. And we propagate the error backwards through the network, backwards pass, and adjust the weights in a manner that reduces the error. And so we're going to use gradient descent, just like in your math class. And this is our optimization strategy, typically used to adjust weights in the network based on the error. It seeks to move the weight in the direction of steepest descent, negative gradient of the error. Now, overfitting and the need for large data sets, neural networks, especially deep ones, have a lot of parameters. This flexibility allows them to model intricate patterns, but it also makes them susceptible to overfitting. Overfitting occurs when a model performs exceptionally well on the training data, but poorly on unseen data. My personal rule of thumb is I want 30 observations for every parameter, and that's true for every single model I build. More is better. But 30, I've just kind of found is like a good, a good number to say, hey, if I have, I want to have at least 30 observations per parameter. All right, so let's go ahead and run through an example. I'm going to use the cover type data set from Kaggle. Now here I'm going to say my target variable is this cover type 1 or not? Because we're focused on logistic regression. This has, I think, 7 levels to it. 2 is the most common, 1 is the second most common in this data set. And I'm just going to say, hey, either it's 1 or it's not 1. It's going to be my binary target variable. I'm going to go through and bin soil type and wilderness area so that I just have one binary dummy variable for the categorical data. And I'm just going through and just doing data prep. And we're going to do Box Cox, Yo Johnson, and median impute on the data. And I'm going to do a train validation test split here. And I always like to have my predictor variables contained in a vector or a list. If I'm working in R, it'll be in a vector. If it's in Python, it's going to be in a list. The most natural way to handle things in pandas. All right, so now if I'm working in R, neural networks are grossly inferior to Python by a large margin. But I feel like R is a good place to learn these concepts. I'll talk about, to me, R is the better platform for data science as a whole, but there are some lanes where Python is just substantially better. Text analytics and machine learning is where it's better. In my opinion, everywhere else, R. And I will debate that if you want. So let's go ahead and run through this. I'm going to use the nnet package with its namesake function to do a neural network. A disadvantage of this is that this only allows one hidden layer for my neural network. And so I don't have like the multiple layers. I can't do deep learning with this. I think this is fine for what people in the statistics lane tend to be tackling. But there are some there's some shortcomings that this is a pretty fast function and it works pretty well. I want to see something. Yeah, all right. Now here I'm just going to go through and I'm naming my neural network models by the number of hidden nodes that they have. So I only have one hidden layer, and I'm going to go through, and the number of nodes in that layer is going to be the name, and I'm going to pad it with 0 to make sure that I have, like dictionary order matches the actual numeric order. All right, so let's go through and visualize the neural networks. Unfortunately, the best visualizations for this are, it is contained in a package, but I couldn't remember the name of the package. But I know that here, this website will give me the neural network plot that I'm looking for. And so here I want to show you what it looks like. So here I made one with just one hidden layer node. And you can see that I've got my generalized linear model going into the hidden layer, and then I have a single predictor variable and the intercept going into my output, which is cover. Okay. And so now let's say if I have 2, and I'm going to go with the Fibonacci numbers for the number of hidden nodes. And so, you can see it just increases. So I've got for 3 generalized linear models, cumulatively coming together to give me 1 neural network. And now 3, 5, 8, 13, 21, 34, and now it's so much I can't even see. This is very wide. My experience in general is that the square root of the number of predictor variables is going to be is going to give me practically all the accuracy I'm going to get. And so here that would be like 3 or 4. So I would expect like maybe this one or this one to, practically speaking, give me as much accuracy as I'm going to get. So let's see what happens. And so yeah, you can see it, it eventually just, it just gets nuts. It can't even, the picture can't even show what's going on. All right, so now let's look at the number of weights and number of coefficients, and you can see that, so no, the number of observations per coefficient is what I've got here. And this is a way to check to make sure that I'm not setting myself for overfitting. So when I have 71 hidden nodes, I've got approximately 195 observation per parameter to work with. And so that's actually not quite right because of the bias, but that's just 2. So this is pretty close. And so this is a way for me just to kind of say, hey, am I pushing the envelope on the overfitting aspect? If I was to see like 5, some small number or a fraction, I would say, hey, I'm prone to overfitting. I'm going to back off. All right, let's get the predicted values. And I'm going to create a generalized linear model just so that I have a benchmark to compare to. And so here, this is a logistic regression model. So it's a generalized linear model, and it's it is effectively a neural network with no hidden nodes. And let's go ahead and compare model performance. All right, so we can see that on my validation set, 46 is the best one I got. And that was only 2. So I said, 3 or 5 is where I expected to get the best. Well, let's see. 3 was, second best, and 5 ends up being around like average. But so like, it just shows that you don't need a whole heck of a lot to achieve your goals off of this. So the of all the models I built, the GLM is the least complicated, then 0, 1, then 0, 2. The least complicated model, the third least complicated model, is the one that gave me the best performance on my validation set. And when I look at train and test, that can, I see consistent results. I noticed that the training statistic looks close to the validation statistic, up to rounding it, they're the same. And so I don't think I have to worry about overfitting. And so, you know what, so I would definitely want to go with the O2 on there. And this is the mean absolute error. All right, now here is for, let's scroll back up on this. I want to take a look. Yeah, and now let's look at the actual accuracy. In terms of accuracy, I have the 71 is the most accurate. 80 we got 0.8 for 55, but you'll notice that things are all pretty tight. So the number 5 is definitely up in the running for being, so if I consider the number of parameters, the complexity, and the risk of overfitting, 5 looks pretty decent to me. Like it's not the best performing model, but for the fact of how much simpler it is than the others, this is a much, this is probably the one I would actually launch into production, is the one with 5 nodes. I wouldn't put 3 into production. I'm kind of surprised by this one. All right, here, let's go ahead and take a look at our model for the ROC curve. And so, like, yeah, this blue is definitely one we would not put into production. Look at that. That is not the baseline for reference. That is actually model 34. Wow, that's horrendous. Now here 3 is looking pretty bad. All right, so neural networks are a generalization of generalized linear models. In fact, they're a collection of generalized linear models. I think of them as a tangled bag of generalized linear model. They're super powerful. They can do amazing things when we're talking about non-traditional data, non-spreadsheet data. They they have a lot of power, a lot of utility. There's a lot of shortcomings with them. They're super black boxes. It's like, why did it do that? I have no idea. They tend to overfit. They require more data prep. They can't handle missing values at all. So there's a lot of shortcomings with these, but they have a lane. They have a spot to use them, and so this is why they're so popular. People love to talk about them on the internet. And so they're definitely going to be sticking around for a while. All right, well, that's all I've got for you. Life is short. Do math.